Hello there. Thanks for tuning in to the second episode. Today's topic is going to be the membrane potential, which is the mechanism by which your neurons can use electricity. I know it seems like it's just a small topic, but it is a crucial piece to understand exactly how we get anything done around here. By the end of the video, you should be able to answer the question, what is a membrane potential, and what does it do? A lot of the times, we think of our neurons as little wires sending electricity from one side to the other, but interestingly enough, that's not exactly right. Charge actually goes in and out of the cell in a way that is carried across the axon. This sounds kind of complicated because it kind of is. The mechanism by which the cell sends electricity boils down to manipulating the membrane potential along the axon using the power of ions. Casting our mind back to chemistry, an ion is what you get when an atom gains or loses an electron, giving it a net charge. The major ions in the body are going to be potassium, sodium, calcium, and chloride. If we take electricity as a simple movement of charge, we can start to see how manipulating the concentration of these charged particles can be leveraged for neuronal activity. Look at this model of the membrane of an axon. The inside of the cell and the outside of the cell have different amounts of our ions of interest, and the stored energy of this separation of charge across the membrane is called the membrane potential. A way to think about this is with two rooms with a door between them. If one room is really crowded with a lot of people, and we open that door, a bunch of people will run to fill the space that just got opened up. We could then siphon some of the energy of the movement of the people for our own needs. This raises the question, how do we set up the membrane potential packing the first room in the first place? Like the walls between the rooms, the phospholipid bilayer of the cell membrane doesn't allow charged particles to slip through, so there has to be other ways for ions, or people in our analogy, to get across. These quote-unquote doors come in two classes of proteins, ion channels and ion pumps. Ion channels passively allow ions through the membrane. No energy required. However, they don't just allow any old molecule to come through. Channels are selective in what is allowed to pass. For example, a potassium channel only lets potassium ions in, even when sodium ions have the same charge. However, there are some nonspecific cation channels that let different positively charged ions through. Another interesting property of ion channels is their ability to be gated. While some channels are always open, there are a whole host of channels that need certain conditions to be met to allow things through. Examples of gating include voltage gating, where a specific voltage is needed for opening, ligand gating, where something has to bind the channel to open it up, or mechanical gating, where some mechanical force causes a deformation to open up the channel. So, ion channels have selectivity in what comes through and some control of whether they're open, but the direction is not controlled. Ions simply flow down their gradient. But when our neurons are at rest, we don't see an even amount of ions on the inside and outside. For example, the sodium ion concentration outside the cell is 10 times as much as the concentration inside the cell, and the calcium ion concentration is 10,000 times greater on the outside compared to the inside. We can't reasonably expect to open up our channels and hope these ions will naturally make such a steep gradient. We need some way to build this gradient. Enter ion pumps, the mechanism by which your neurons establish the ion gradient, which in turn gives the membrane potential. Pumps transport ions against their gradient, from low to high concentration. This takes energy, which is provided by ATP, meaning ion pumps are engaging in active transport. The most famous and important ion pump is the sodium-potassium pump, which works to establish a high potassium concentration inside the cell and a high sodium concentration outside the cell. A significant portion of all the energy you will ever use is invested in this one pump. Ion pumps make the gradient that ion channels take advantage of during communication. I've given you a bunch of abstract information, but scientists learned about these things through a lot of careful study and experimentation. Since we're dealing with charges here, we can calculate the potentials for ions in the cell, which combine to yield the membrane potential of the cell itself. The first important equation is the Nernst equation, which gives the equilibrium potential, E ion, for a single ion. The equilibrium potential of an ion is equal to the ideal gas constant times the temperature in Kelvin over the charge of the ion multiplied by Faraday's constant, with the whole quantity multiplied by the natural log of the ratio between the concentration of the ion outside and inside the cell. You may also see a change of base to a logarithm with base 10, which adds a 2.303 to the start. E ion is not the membrane potential, but the combined effect of all E ions in the cell gives the membrane potential. The second important equation is the Goldman-Hodgkin-Katz equation, which incorporates potassium, sodium, and chloride ions to give membrane potential. The first half is similar to the Nernst equation, with the argument in the logarithm being different. We have to introduce a calculated value called the relative permeability to account for the fact that certain ions are much more permeable to the membrane due to differing amounts of ion channels in the membrane. Think of this permeability term as a weightage for how much effect each individual ion has on the overall membrane potential. Another important thing to note is that though the GHK equation doesn't have a z term for charge in the fraction, we still account for chloride's negative charge by flipping the concentration inside and outside terms. Alright, today we covered membrane potentials, a vitally important property of neuron membranes. We got to see how ions interact to make it, how the membrane proteins facilitate the movement of ions, as well as equations we can use to quantify potentials. Just like last time, I left timestamps and other information in the description below. Next time, we'll start tackling how neurons communicate with each other using membrane potentials, so don't worry about not getting it 100% on the first go. It's going to come back, and we'll cover it again. Thank you for watching, and I hope to see you next time.